Hey guys, in this video we're going to talk about Chapter 15, Section 1, Critical Points, Local Extrema, and Saddle Points. Alright, so we talked about this in Calculus 1. We talked about finding local maxes and mins and absolute maxes and mins. In this video we're only going to talk about local maxes and mins when we have two independent variables. But just to reintroduce you to this idea a little bit, a local max is going to be basically anything that is at like a hump of a curve. So basically a local max means that all the points around it are lower than it, and a local min, on the other hand, means that all of the points around it are higher than it. So points like that and like that. The absolute max, which we're going to talk about more next time, is the absolute highest point on the graph for a given interval, and the absolute min is the absolute lowest point in the graph for a given interval. Now, the absolute max and the absolute min are also local maxes and local mins just by definition. Okay, so recall from Calc 1, how did we figure out local maxes and mins? What we did is we had a function, we took the derivative of the function, and we set it equal to 0 to get the critical points. And then with the critical points, we took the derivative of the function, took the derivative again to get the second derivative, and plugged in the critical points to see whether we got a positive number or a negative number. If we plugged in the critical point into the second derivative and got a positive number, then we had a local minimum, right? Because what the second derivative tells us, if it's positive, it's concave up, and if it's negative, it's concave down. So if we plugged that critical point into the second derivative function and we got a negative number, we knew that we had a local max because this thing is concave down. And then the unfortunate situation happened once in a while where we took the second derivative and we got 0 when we plugged in the critical point, and that told us nothing about whether or not there was a local max or min there. There could have been a local max or min there, but because the second derivative is 0, that's not going to tell us anything. Okay. So I'm not going to do this example in full just for the sake of time, but just to remind you what we did, we had a function with one independent variable in Calc 1. Remember, we had f of x equals x to the third minus 3x, something like that, and we were given some interval, and we were asked to find the local max and min and the absolute. I'm not going to look at the absolute on this video. We're going to talk a little bit about that more next time. But for the local, what we did is first we found the critical numbers, and the intuitive idea behind the critical numbers is we're basically looking for places on the graph where the slope is 0. So slope is 0 means flat, right? Flat lines. And so we're looking for these points in particular, these points where the tangent line to those points is flat. So the idea behind that is take the derivative, right? That's the slope of the tangent line, and set it equal to 0. Okay, that's the flat slope. So if we take the derivative of the function f prime of x, we got 3x squared minus 3, and then we said, okay, I want to see when that slope equals 0 to see where these flat lines occur. Okay, these flat tangent lines. So we took that, we set it equal to 0, and we solve for x that way. And so we got x squared equals 1, take the square root to get x is plus or minus 1. So those were our critical numbers. And the way that we use the second derivative test, we took the second derivative. So the second derivative of this guy was 6x. Then we plugged in each critical number in for x. We plugged in plus or minus 1. And when we plug in positive 1, we get a positive number. So that tells us that this thing is looking like this. So we have an absolute minimum, and we can see that from the graph right here. This is at x equals positive 1. And when we plugged in x equals negative 1 into the second derivative, we got a negative number. And so we had something that looks like this, concave down. And that corresponds to this guy right here. So we're going to do something very similar in this section, except we're going to extend this notion of critical numbers into functions with two independent variables, right? So we have x and y as our independent variable. And so what this amounts to is figuring out how we're going to define critical numbers, because remember, we no longer have this idea of a derivative at a point, right? We have directional derivatives. But let's delve into what we're talking about here when we talk about critical points on surfaces. Okay, so here's Calc 3. This is where we are now. Hopefully, we're all here now. But this is the idea. So we have some surface, right? And a surface is always defined by two independent variables, typically x and y, right? So we had z equals f of xy. Now, very similar to the definition of a local max with one independent variable, we say that a surface, or a graph of a surface f, has a local max at a point p naught if f of p naught is greater than or equal to p for all points p near p naught. Now it's intuitive if you think about it, because so we have this local max right here, and basically what this definition is saying is, hey, all the points around this guy had better be smaller than it. That's what this definition says. Z values, right? We're talking Z values because, and when we talk Z values, we talk about height. So we're talking about all of the heights around that point are smaller. In a similar definition is the local min, right? So if we have a local min, such as something right here on the graph, all of the points around it are going to be higher than it. That's what this definition says. It says if we have a local min at p naught, so if that's p naught, then all of the points around it, all of the p's around it, when we evaluate it at that function, we get a height. All of those heights around it had better be bigger than it. Okay, that's what that means. So pretty intuitive definitions here: local max, local min of a surface, and of course the absolute, which we're going to get more into next time. Sometimes we call it global. I can't remember in Calc 1 if I called it global or absolute, but they mean the same thing. Basically, that's the absolute highest point on the graph. It's the absolute max. The absolute minimum is the absolute lowest point on the graph. More on that next time. Here we're just going to talk about the local, so those humps. Okay, so here's the issue. We need to come up with a way to define a local max or min on a surface, right? We know what to do with a function with only one independent variable. So we had functions f of x, and those were just curves, right? And local maxes or mins were just these humps, right? And so to get those critical numbers, what we did is we took the derivative of the curve and we set that derivative equal to 0 to get those tangent lines equaling 0. That's when the slope equals 0. That's what we did. So what we're going to do now is we're going to use the gradient vector, okay? And so remember from a few lectures ago, we first introduced the gradient vector. The gradient vector points in the direction of maximum ascent, maximum slope, okay? So given any point on a surface, the gradient vector through that point is going to point in the direction of maximum increase, okay? The steepest hill that you can go up on any point, okay? So what we're going to do is we're going to use this gradient vector to talk about our critical numbers in 3 space. R3, 3D, okay? All of those things mean the same thing. Okay, so what we're going to do is we're going to remember that a gradient vector points in the direction in which the function increases, right? That was the direction of maximum ascent, maximum slope. And suppose that a function f has a local max at a point p naught. So on the graph, I've labeled it here. That's our local max, and in this case, it's actually our absolute max as well. If the gradient of f of p naught were defined and non-zero, then we could increase f by moving in the direction of the gradient vector, okay? So if there was a gradient, we could move in that direction to increase the height on this curve. But if we're at the very top, can we increase the height? Well, the answer is no, right? So since f has a local max at p naught, there is no direction in which f is increasing, right? There is no direction we can take from this where the function is increasing. And so we conclude from that the gradient of f of p naught is equal to the zero vector, okay? So that's the big idea. We are going to be finding where the gradient is equal to zero to find our local max and our local min. The local min has a similar idea. The idea is this. Let's suppose that we have a local min at p naught. If f of p naught were defined and non-zero, or if I should have said the gradient here. So if the gradient of f of p naught were defined and non-zero, we could decrease the function f by moving in the opposite direction to the gradient. Okay, so that's the same idea. If we did have a gradient, okay, at p naught, that would be a vector that would point in the direction of maximum slopage. Okay, maximum slope would point in that direction, maximum ascent. And theoretically, we should be able to go backwards down that gradient in the opposite direction to decrease, but we cannot because we're at a local min. And so in this case, the gradient is also equal to the zero vector. So that's the big idea here, you guys. The gradient vector is going to allow us to find local maxes and mins by setting it equal to zero. This is a very important idea here. Points where the gradient is either zero, the zero vector, or undefined are called the critical points. So this is the analogous definition to the Calc 1 definition. Instead of taking the first derivative and setting it equal to zero, we are taking the gradient and setting it equal to zero. Now the gradient is composed of two parts, right? It's composed of the partial derivative with respect to x, and it's composed of the partial derivative with respect to y. So we had this definition, we had the gradient, or maybe I'll just use the words. We had the gradient of f was equal to partial derivative of x at a point I plus partial derivative with respect to y at a point j. Now here's the idea. In order for this whole gradient to be the zero vector, we want this to be zero, and we want this to be zero. That's the big idea. What we're going to do to find critical points is we're going to find the partial derivative with respect to x, set it equal to 0, find the partial derivative with respect to y, set equal to 0. And those are going to give us our critical points, because when those two things are true, the gradient is the zero vector, 0i plus 0j. Okay, so that's the idea. So now it's just plug and chug. Okay, so we're going to find and analyze the critical points of this function. I believe this one is from your book. So what we're going to do is we're going to find the partial with respect to x. We're going to find the partial with respect to y, set those guys equal to 0, get our solutions. Okay, partial with respect to x, I'm treating y like they're constants. So we have 2x using the power rule, minus 2, again using the power rule. All of this goes to 0 because those are all constants with respect to x. Now for y, all of these are constants with respect to y. This becomes 2y by the power rule minus 4 by the power rule. All right? So what we're going to do is we're going to set each of these guys equal to 0. Okay? So when I solve for x over here, I get x is equal to 1. And when I solve over here, I get y is equal to 2. So what I have is a critical point and what do critical points tell us? Well, there's 3 different things it could tell us. Well, actually there's 4, but the 3 big things that we're looking for with critical points is local max, local min, and something called saddle points, which we're going to introduce in a few slides. Saddle, like literally like riding a horse saddle. Okay, and you'll see why they're called saddle points. But this is where the critical point is, and let's actually look at the graph and see what that critical point means. Okay, so here I have the graph on GeoGebra. So I graph the function. When I put in 1, 2 into this, I get z equals 0, I believe. Was that it? Yeah, I get z equals 0. So I literally just plugged all of this stuff 1, 2, 0 into GeoGebra. I got my little point right here. That's my critical point. And what we can see from the graph is that that guy is a local minimum, right? That relative to that guy, everybody else is higher than him on both sides, in the x direction and in the y direction. Okay, so that's a local minimum. And we're going to talk about how to find local minimums without even looking at the graph in just a bit. But let's get some intuition with the graph first, okay? Okay, so we have a function here, and we want to figure out what the critical points are. So we need to take the partial with respect to x, the partial with respect to y, and set those both equal to 0. Alright, so this guy, with respect to x, I can actually write this with the square root in the power, or the 1/2 in the power rather. So I have negative x squared plus y squared to the 1/2. And if I take the derivative of this guy, I have to use a chain rule. So I take the derivative of the outside function to the negative 1/2 times the derivative of the inside with respect to x. So the derivative of the inside is just going to be 2x, right? Because the y is 0. It's a constant. So if I write this a little bit neater, the 2x over negative 2, so this is negative 1 over 2 times 2x, that just becomes negative x. Okay, so this becomes negative x over the square root. I'm just, again, rewriting this as the square root, but since it's a negative power, it's coming under the denominator, just to be consistent with what's in your book. But anyway, that is our partial with respect to x. In a similar way, the partial with respect to y is negative 1/2 x squared plus y squared to the negative 1/2 times 2y this time. So I'm going to have negative y over the square root of x squared plus y squared. Alright, setting these two things equal to 0, I get x equals 0, y equals 0. And if both of these are simultaneously true, notice that we have undefined derivatives because they make those denominators 0. So anyway, 0, 0 is a critical point. And is it a max? Is it a min? Is it a saddle? Who knows? We have to look at the graph. Here's the graph. Put it in GeoGebra, and our point 0, 0, 0 is literally right at the tip of that cone. So that guy is higher relative to everyone else, and so this is a local max at 0, 0. Okay, so we want to find and analyze any critical points of this function g of xy equals x squared minus y squared. Alright, so critical points, we want to make sure both of these partials are equal to 0, right? Because that's what makes a gradient 0. So if I take the partial with respect to x of this function, I simply get 2x. Partial with respect to y is simply negative 2y. Setting each of these equal to 0, I get x equals 0, y equals 0. Okay? So 0, 0 is a critical point. Could be a max, could be a min, could be a saddle. What's a saddle? Okay, what's a saddle point? Well, a saddle point literally looks like a saddle that you throw it on a horse, you ride the horse, saddle point. Okay, basically what it means is that there's a max in one direction, either the x or y direction, and there's a min in the opposite direction. So like here, we can check out this saddle point is right here at the origin, 0, 0, 0. Now keep in mind, green is y and red is x. Okay, so if I start at the saddle point, if I start to move in the x direction, look what happens. Let me see. Look what happens. When I start to move along the x direction, I'm increasing, right? In either x direction, I'm increasing. But as I start to move along the y direction, I'm actually decreasing. So there's no absolute max or min because the directions, the x direction, the y direction, it's increasing in one direction, decreasing in the other. When that happens, we call it a saddle point. Whereas with the absolute max and mins, it was decreasing in the y direction and decreasing in the x direction. Or, increasing, either one. But saddle, it's increasing in one direction, decreasing in the other. So this is a saddle point. 0, 0 is a saddle point. And we're going to look at ways to do this algebraically without even needing a graph. And this is it. So this is an important slide. All right, this is an important slide. And I'm not going to go into how this formula was derived. It's just a lot to explain. It's a lot to talk about. And I don't know that it's necessary. So if you are interested in how these things were derived, come talk to me, watch a video, read the textbook, all of these things. We can talk about how these things came to be. But for now, I just want you to know the formula so that you can use it, so that we can find the local maxes and mins. Okay. So anyway, suppose that we have this point on our function, and we take the partial derivatives, set them equal to 0, and we get that the gradient is 0. Okay, we find those x and y values. Then we have this new function d. D is equal to, I'm going to explain what each of these things mean. This is the second partial derivative with respect to x, hence the two x's. So this is second partial with respect to x. Okay, this is the second partial with respect to y. And this guy is the partial with respect to x, then the partial with respect to y. So we're going to do a bunch of examples so you guys can see how this goes, but it's really just like taking derivatives in one independent variable. You're literally just taking the derivative twice for these. But it's not too bad. I'm going to show you. I know it's like a lot on this screen, but we're going to do a bunch of examples so you guys can get the hang of it. But these are the conditions that we're going to use to determine if we have a critical point that is a local max, a local min, or a saddle point. And this is the unfortunate event where we aren't given any information and we have to use other means to figure out if we have local maxes, mins, or saddle points. So copy this stuff down and we're going to go ahead and use it for this next example. Alright, so with these problems, what I like to do, we have a bunch of stuff to find, okay? We have first of all, we want to figure out what the derivative with respect to x is. we want to find the double derivative with respect to x, the second derivative. We want to find the derivative with respect to y. We want to find the double with respect to y. And then we want to find the derivative with respect to x and then with respect to y. Alright? So we want to find these things. We also want to find our d. And we also want to find our critical points. Alright? So I'm going to start by finding the stuff up here and then moving down, okay? So the partial with respect to x, we know how to find that. We're just looking at this guy and we're taking the derivative with respect to x. So that is going to be 4x to the third. And then for this guy, keep the first times the derivative of the second plus keep the second times the derivative of the first. So it's just negative 4y. Okay, so that is the partial derivative with respect to x. Now, the double, it's like Calc 1. I just take the derivative of that guy again with respect to x. So, derivative of 4x cubed with respect to x is 12x squared. This goes to 0 because y is a constant. We're taking the derivative with respect to x. So this is 12x squared. Alright. Now, with respect to y, again, we're treating x like it's a constant. So with respect to y, we have 4y to the third. And then this guy, keep the first times the derivative of the second. Plus keep the second times the derivative of the first. Okay, so that's just negative 4x. Okay. Alright, so then the double with respect to y, I'm just taking the derivative of this guy again with respect to y. So this becomes 12y squared. This goes to 0 because we're treating x like it's a constant. Alright, now let's do this guy right here, fxy. So, take the derivative with respect to x, which I already did here, then take it with respect to y. So I'm looking at this, and I'm taking it with respect to y next. So with respect to y, this is just negative 4, because this is all 0, right? It's a constant. Derivative of negative 4y with respect to y is negative 4. So that's my answer there. Alright, cool. We have all of that. We can find d. So look at your notes and see what d equals. So d is equal to fxx, or double derivative with respect to x, I guess, second derivative. I know it's not the technical terminology, but it's how I remember things. So double times double y minus fxy, which is just negative 4 squared. Okay, so this is just the formula for d. Look back in your notes. This is the formula we're using up here. Cool. Alright. Critical points. How do we find critical points? With the first partial derivatives. Set them equal to 0. So we have fx equals 0, and so we have 4x cubed minus 4y equals 0. We also have we also want to see what happens when the partial with respect to y equals 0. So we have 4y cubed minus 4x equals 0. So this is just how we find critical points. We take the first partial derivative with respect to x and with respect to y and set them equal to 0. That's how we did it in the previous slides. That's how we find our critical points. Okay, so let's go ahead and find them. Notice that we have two equations with two unknowns, and we can definitely solve something like that. So what I'm going to do first is I'm going to look at this guy, and I'm going to isolate him in terms of y so that I can plug that into here, because I want one variable so that I can solve. I want numbers here, right? This is just a system of equations, two unknowns, we can solve it, all right? So if I isolate y. I get 4y on one side just by adding 4y to both sides, equals 4x cubed. Then I'll go ahead and divide both sides by 4 to get y is equal to x cubed. Alright, with this relationship, I can plug that in, here, right? So I get 4, and instead of y, I'm replacing it with x cubed. Cubed minus 4x equals 0. Alright, so I have, for this guy is just x to the 9th minus 4x equals 0. Now I can factor out of 4x. And when I do that, I get x to the 8th minus 1 equals 0. So I get 4x equals 0, and I get x to the 8th minus 1 equals 0. Solving on the left, I get x equals 0. Solving on the right, I get x equals positive or negative 1, right? Because x to the 8th equals 0, either 1 or negative 1 will make that a true equation. So both of those are valid. Okay. So these are my options. I have x is 0, x is plus or minus 1, and I want to go back into this equation and see what my corresponding y values are for those x's. So for x is 0, when x is 0, I get y equals 0 cubed, which is 0. So one critical point is 0, 0. X is 0, y is 0. The next critical point, I'm going to look at when x is negative 1. Well, when x is negative 1, y is negative 1 to the 3rd, which is negative 1. So a critical point here is negative 1, negative 1. And my third critical point is when x is positive 1. Then y is equal to positive 1 to the 3rd, which is 1. And so my third critical point is 1, 1. So let's go ahead and rewrite that up here so that we can stay organized. So my critical points, we have 0, 0, we have negative 1, and we have 1, 1. And we want to figure out, with all of these conditions circled in gold, we want to figure out if these points correspond to absolute maxes, mins, or saddle points. And we can do this all algebraically, which is pretty cool. So, let's see. Now, I'm going to take all of these points, first of all, and plug them into D. Because I'm doing this first for the following reason. If I get that D is negative, automatically saddle point. Okay? If it's negative, saddle point. Alright, so that's going to be nice. So, first of all, I'm gonna check for apps max, min, and saddle. I'm checking this. So the first, I'm going to check this one first, 0, 0. So I'm going to plug in 0, 0 into D when x is 0 and y is 0. So when I do that, I get 12 times 0 squared times 12 times 0 squared minus negative 4 squared. Okay. So this goes to 0, 0, and we have 0 minus 16, which is negative. Right off the bat, saddle. Because it says if D is negative, then F has a saddle point at that point, at the critical number. So, we have a saddle point. So this is I'm going to just write it up here. This is a saddle point. Now let's check the other ones. We have 2 more to check. Let's check negative 1 next. So x is negative 1 and y is negative 1. And we're just we're just plugging this into D. So we have 12 times negative 1 squared times 12 times negative 1 squared minus negative 4 squared. Okay, so this is giving me 12 times 12 minus 16. This is positive. Okay, so we have two choices. We can either have choice 1 or choice 2. The next thing we need to look at, if we get a positive output for the D function, we need to look at the second derivative and with respect to x and see if it's positive or negative. All right, so let's do that. So we need to check, we need to next check f(x(x) of negative 1, negative 1. Basically, we're just plugging in x is negative 1, y is negative 1 into the second derivative with respect to x. Now we don't have any y here, so it's just 12 times negative 1 squared, where x is negative 1. This is a positive number, and so since I have positive for D, positive for double x, this is the correct one right here. Positive D, positive double x. So then f has a local minimum at that point. All right, so we can say that this guy is a local minimum. And finally, we need to check 1, 1. This does get easier with practice. I know it's kind of a pain, but it can be kind of fun if you look at it the right way. So we're plugging in 1 for x and 1 for y into our D function. Again, we're checking this to see if it's absolute max, absolute min, or sorry, not absolute, local max, local min, or saddle point. Okay, so this is positive times positive minus 16. 144 minus 16 is positive. So since that's the case, we need to check the second derivative with respect to x at 1, 1. And again, that second derivative was 12x squared, so we're just plugging in x is 1. So we have 12 times 1 squared. Again, this is positive. So once again, because both of these are positive, we have a local minimum at that point. Okay, so we have a local minimum here. So all of this that we just did was for this. We found the critical points. That's the first thing we did. Once we had the critical points, we plugged those points into this D function that was made up of all of these things up here. And the D function would tell us if we had a saddle point if it was negative. If it was positive, it said, okay, well, you need to check this other condition, the second derivative with respect to x, to see if it's a local max or min. And it turns out we had a saddle point, local min, and what you should do is check the GeoGebra graph. Check the graph of this guy up here and see if this matches with what we got here. Okay, so this is how we do this purely algebraically. Alright, let's try this one. I do encourage you to pause the video, see if you can do this one. First thing we're going to do is find all of our stuff. fx, f double x. And I know I'm not using the formal terminology here, but I don't know. fxy. Gotta find D. Gotta find the critical points. These are all the things we need. Alright, first of all, first derivative with respect to x. Okay. This is going to be x. Hopefully I think I'm going to be able to skip a lot of these steps because you guys should know how to take derivatives by now. So hopefully that's okay. If not, you guys should go back to the power rule and the product rule in my Calc 1 playlist on YouTube. Anyway, I'm going to assume that you guys are experts at taking derivatives. Okay, so we got x, and then this guy, is just going to be negative 3y minus 9. Okay. Alright, and then for the other one, so if I take the second with respect to x, I just get 1. If I take the derivative with respect to y, I get 9y squared plus 18y minus 3x plus 9. And the second with respect to y is going to be 18y plus 18. And finally, fxy. Take the derivative with respect to x. We already did that. Now take it with respect to y. So that's just, if I take the derivative of this with respect to y, it's just negative 3. Okay, cool. Alright, so we got all that information. Let's go ahead and find d by using this formula right here. Okay, so let's see. I have double x, so that's 1 times double y, so that's 18y plus 18. Minus this guy squared. Okay. Oh, I did this in the wrong place. This is supposed to be up here. Okay, so that's that. Let's go ahead and figure out our critical points next. Remember how we did that? We took first derivative, set equals 0, take the second derivative, set equals 0. That whole, both of those combined make the gradient equal 0, so that's why we're doing this. So, first derivative was up here. So we have the system again. We have x minus 3y minus 9 equals 0. And then we have this guy. We have 9y squared plus 18y minus 3x plus 9 equals 0. Okay, so I'm going to work with the easier looking equation first. I'm going to work with this guy. I'm going to go ahead and solve for x. So I'm going to go ahead and solve for x by adding the 3y and the 9 to both sides. So this is x. And now I'm going to just plug that in here into the second equation. This is just solving systems of equations. No biggie. So I'm literally just substituting what I just found here into the second equation. And then I'll simplify. That equals 0, by the way. Okay. So I'm right here. Now I can combine like terms to give me 9y squared plus 9y. Let's see. Negative 18 equals 0. Okay. So what I can do at this point is I can divide out a 9 by everybody to get rid of that 9. Hopefully that makes sense to you guys. Or, you know, you can look at it as factoring out a 9 and then dividing. But either way, you're going to get 9 squared plus y minus 2 equals 0. And I can factor this into y plus 2 times y minus 1 equals 0. So I get the following. I get y equals negative 2 or y equals 1. Okay? So now that I know what y is, I can plug both of those in there to get my corresponding x values. So when y is negative 2, x is 3 times negative 2 plus 9. Make sure I'm doing this. So yeah, x is going to be negative 6 and 9 makes a positive 3. So we have a negative 2 comma 3. Oh, I did it backwards. 3 comma negative 2 as a critical point, right? That corresponds to y being negative 2, x being 3. Now for the other one, I'm just plugging y in here to get x. X is 3 times 1 plus 9. So x is 12. So when x is 12, y is 1. So my other critical point is 12 comma 1. So these are my critical points. And what I'm going to do is I'm just going to transfer them back up here, because that was like side work. The whole point is to see where the absolute, or I keep saying absolute, the local maxes and mins are. These are my 2 critical points that I have. Okay, now that I have that out the way, we can plug in these critical points into the D function to see if I have any saddle points. Right? D has to be negative for there to be saddle points. So this is the annoying part. Finding the critical points is always a pain. But what we're going to do is we're going to first test this one. We're going to say, okay, so we're going to test D of 3, negative 2. And I'm just plugging in 3 for x, negative 2 for y. Of course, there's no x here, so I'm just plugging in negative 2 for y. So that's going to give me 18 times negative 2 plus 18 minus 9. Negative 36. Gotta get the calculator here so I always do like little simple mistakes and it messes me up. So I'm just gonna suck up my pride and use the calculator. Alright, so here's the good news. We don't have to do any more work because this is negative, which tells me that this is a saddle point. So, this is a saddle. Now we gotta test this one. Remember, if it comes out positive when we put it into the D function, we have to do that other step. We have to see whether it's positive or negative when we put in the second x derivative. But with the saddle, we just stop there. So let's test 12(1) now. So test, doing D of 12(1). So I'm just plugging in 12 for x. Of course, there's no x. 1 for y. So I get 18 times 1 plus 18 minus 9. And that's going to be positive. This is a positive number, 36 minus 9. So since D is positive, I need to consider option 1 and option 2. Now we have to take a look at the second derivative with respect to x and see if it's positive or negative. So we do have to check this guy at 12(1). So if I plug in 12 and 1 into my second derivative, well, that's just positive always. We don't have anything to plug in. So this is positive. This was positive, and so going back here, this guy, condition 1 is met, so this is a local minimum. And that's it. That was the whole point of this, to find those critical points and use the critical points in our D function, in our second derivative with respect to x, to determine if it's a saddle, local min, or local max. And it turns out we don't have a local max here. We just have a saddle and a local min for this function. Again, I encourage you to check this out on GeoGebra and see that this algebraic finding confirms what you're seeing visually. Okay. Alright, this one's kind of interesting, I think. So we have this function, the surface, x squared minus cosine y. And if I find all of my things, fx, fy, f double x, f double y, and fxy. All right, first derivative with respect to x is 2x. First derivative with respect to y, derivative of minus cosine is positive sine. Okay. Double with respect to x is 2. Just taking the derivative of that. Double with respect to y is cosine. And finally, derivative of x is then with respect to y, that's just going to be 0, okay? Because, again, 2x, we're thinking of it as like a constant. So when we take the derivative of 2x with respect to y, it just goes to 0. All right, now that I have all of this stuff, let's consider the d function. So the d function, we have our second with respect to x is 2 times second respect to y is cosine y minus 0 squared, which is just minus 0, which is 0. Okay, excellent. Now for our critical points. So we take first derivative with respect to x, set it equals 0. Second derivative with respect to y, set it equals 0. Here, x is 0. Here is interesting, right? This is kind of interesting. I think it is. Because this is a this is a cyclical function, which means that we have infinitely many inputs that will make this function true. Think about your unit circle. Think about all the spots on your unit circle where sine is 0. It happens here at 0. It happens here at pi. It happens again at 2 pi. It happens again at 3 pi. It happens again at 4 pi. It happens forever and ever, right? Any angle that's coterminal to pi and 2 pi are going to be in this solution set. It's going to satisfy that equation. Sine of pi satisfies that equation. Sine of 100 pi is going to satisfy that equation. Sine of 1,000,000 pi. There's infinitely many possibilities here. So what does that mean? Well, we're not going to have just a singular y value that solves this. It's not just going to be 0. I mean, we didn't restrict any kind of domain yet. I mean, we could. But the idea here is that all y's that satisfy this are in the form of 0 plus pi k, where k is an integer. Okay, so k is an integer. Okay, and all this means is, if we let k equal 0, 0 plus pi times 0 is 0. That's in the set. If we let k equal 1, 0 plus pi times 1 is pi. That's in the set. K equals 2. 0 plus pi times 2 pi. 2 pi is in the set. That's what that means. This is an infinite set here, okay? So I guess the idea, so what we're trying to do is find local maxes and mins, right? That's what we're trying to do at the end of the day. And and we have this function right here. And so, this is going to change depending on what y is, right? If we test y equals 0, right? That's the first thing in our set, y equals 0. Then we have y equals pi. And then we have then we have y equals 2 pi, then we have y equals 3 pi, and so forth, right? So our critical point was at 0 and pi k. K was an integer, 0 plus pi k, so it's our critical point. And so if I plug in 0 in here into this d function, I get 2 cosine 0 is positive, and that checks out. And then if I look at the second derivative, which is 2x, I get 2 times 0 is 0. Alright. So what is that telling me? Well, let's see. Well, that's not really telling me anything because that other condition isn't met. So what did I do? I plugged in y equals 0 into this function for y, and I got a positive number. So then I checked out the second derivative with respect to x, and actually I did the wrong thing here. I looked at the first derivative. Let's look at the second derivative. The second derivative is always positive. So the second derivative is always positive. Since we have positive, positive, this is going to be a local min here at 0, 0. What about when y equals pi? If we plug in pi here, we get 2 cosine pi. Well, cosine of pi is -1. 2 times -1 is negative, so that's a saddle point. So that means we're going to have a saddle point at 0 pi. Okay? And you can guess what's happening, right? We're going back and forth between local min and saddle point. Local min, saddle point. The double derivative with respect to x is always positive. It's always positive 2. Okay? But we're oscillating between a positive and a negative value when we plug in something here. So at 2 pi, cosine of 2 pi, so cosine of 2 pi is 1. 2 times 1 is 2. That's positive. So we have positive, positive. Again, we have a local min. Okay, and you can see what's going to happen. We're going to have a saddle point at 0, 3 pi, and so forth. And so we can look at this graph if we want to. It's right here. And so we can kind of see what's happening. First of all, we see the local min at 0. Hopefully you guys can see that that's the lowest point relative to the other points. And then at pi, around 3, right, and around -3, around pi and negative pi, we have saddle points, right? Because if we kind of shift our view and look at the points, we can see that we're decreasing in the y direction, but we're increasing in the x direction. So that's the idea here. Okay, but anyway, this example I just wanted to do because I thought it was cool, because we have this infinite set. We kind of have local mins, local maxes like oscillating, and our local mins and saddle points oscillating back and forth. And so anyway, that was that example. Let's go ahead and do one like this, and I think we have 2 more examples here. So let's go ahead and knock it out. This time we don't have this periodic function, so we should get some nice finite answers here. Let's go ahead and list all of our stuff that we need to find. And then D, and then critical points. Alright, so that's all the stuff we need to find. First derivative with respect to x, pretty easy here. This is just 27. No. I thought it was easy. I jinxed myself. 3 times 3 is not an easy problem. No, I'm just kidding. 3 times, so we have 9x squared. I'm just using the power rule here. Alright. Now this guy is -9. Again, I'm just taking the partial with respect to x, so all of those y's are acting like constants, hence the derivatives are all going to 0. Okay, so double x, if I take the derivative of this guy, it becomes 18x. Yes, excellent. Okay, 18x. What about this guy with respect to y? I'm getting 6y squared minus 36y. Excellent. Double with respect to y, just taking the derivative of that again, is 12y minus 36. And now for this one, derivative of x, we found it, with respect to y is 0. All that I see here, x's and constants, so that goes to 0. Okay? So my d, if you look at your notes, is double x, 18x, times double y, 12y minus 36. Okay, minus this guy squared. Okay. Alright, so now for my critical points, I take this and I take this, set them both equal to 0. Alright, so I have 9x squared minus 9 equals 0, and I have 6y squared minus 36y equals 0. Here, if I solve for x, 9 divided by 9 is 1, take the square root, I get plus or minus 1 for x. Okay, over here, if I set this equal to 0, first thing I'm going to do is I'm going to factor out a 6y, and I get y minus 6 equals 0, so we get y is equal to plus or minus 1. No. Nope. That wasn't right. I get y equals, well, how about this? Instead of doing that, since we already found x, let's plug those x's in here for y. So when x is equal to 1, we get 6 times 1 squared minus 36 times 1. So 6 minus 36, am I getting the right thing here? Oh, no, I can't do that. I'm sorry. That's not in terms of, that's y, that's not x. So we actually do have to do what I was doing before. We need to factor out a 6y. When I do that, I get y minus 6 equals 0. Setting both of these factors equal to 0, I get y equals 0, and then I get y equals 6. Okay. So, so the question is, which, how do I write this as an ordered pair? Well, what this tells me, up here it says x is equal to plus or minus 1, and here y is equal to 0 or y is equal to 6. Okay, so I have the following. I have minus 1 can go with 0. I have minus 1 can also go with 6. I have 1 can go with 0. I also have 1 can go with 6. Okay, so this is plus or minus 1, y equals 0, y equals 6. So those are the possible combinations there. So these are all my critical points, all 4 of these. So let's go ahead and erase some of this, and so we're going to have to test these points. So let's go ahead and do that. So our critical points, we have negative 1, 0, negative 1, 6, 1, 0, and 1, 6. Okay, so the first thing I'm going to do is I'm going to test these points into D to see if I get any saddle points. Those are negative values when I plug them into my D function. So if I do D of negative 1 comma 0, I get 18 times negative 1, okay, times 12 times 0 minus 36 minus 0. Alright, so when I do this, I get negative 18 times negative 36. That is positive. So I need to check the second condition. I need to plug in my point into the second derivative with respect to x to see what that gives me. This guy is 18x, so I just get 18 times negative 1 is negative. So when I have a positive d and a negative second derivative with respect to x, I get a local max. So this guy is at a local max. Okay, so this guy's at a local max. Alright, so I just need to test the other ones. So negative 1 comma 6. Need to test that guy into D. So I D of negative 1, 6. 18 times negative 1 times 12 times 6 minus 36. That is going to give me, let's see, so it's going to be negative 18 times 12 times 6 minus 36 is 36. So that's going to give me a negative answer, which tells me that this guy is a saddle point. That guy is a saddle point. Alright, so next one is 1, 0. So let's test that into the D function. So we have D 1, 0. It's going to be 18 times 1 times 12 times 0 minus 36. And so that is going to give me 18 times a negative 36. That's negative, which means it's a saddle point. So this is also a saddle point. And finally, 1 comma 6. If I plug that into my D function, I get 18 times 1 times 12 times 6 minus 36. And I believe that's going to be positive. So I need to check the double derivative with respect to x. Now we know that's 18x. Our x in this case is 1, so that's going to be positive. 2 positives means it's a local min. So this is going to be a local min. Alright, let's try this one. So first of all, I'm going to find my first derivative with respect to x. Okay, so keep the first times the derivative of the second, 0, plus keep the second times the derivative of the first. So this is y times 2x, or 2xy if you like that. And then over here, this is just going to give me negative 2y when I take the derivative with respect to x. If I take the double derivative with respect to x, I just get 2y. Okay, and if I take the derivative with respect to y, just the first derivative with respect to y, let's see, I get x squared times, keep the first times the derivative of the second plus keep the second. Okay, so I get x squared plus 4y minus 2x. And then if I take the second derivative with respect to y, I just get 4, right? Because the x's are constant. Okay, now if I do fxy, I look at this and then take it with respect to y. So that's going to give me 2x minus 2. Okay. Alright, now D is going to be this guy, so fxx times fyy minus 2x minus 2 squared. Alright, and now my critical points, important part, I take this guy, set equal to 0, so I have 2xy minus 2y equals 0. And then I take this guy and set it equal to 0 as well. Minus 2x equals 0. Okay. So looking at this top equation, if I factor out a 2y, I get 2y, and then in parentheses I get x minus 1 equals 0. So that tells me that 2y equals 0, x equals 1, or x minus 1 equals 0, so x equals 1, and so here y is equal to 0. So what I have is y equals 0 or x equals 1, okay? And then if I plug in y equals 0 into this guy right here, I get x squared plus 4 times 0 minus 2x equals 0. So I get x squared minus, okay, so again, this was when y was equal to 0. So then I get x squared minus 2x equals 0. Factoring out an x, I get x minus 2 equals 0. So I get x equals 0, x equals 2. So when y equals 0, I have two possibilities for x. So my critical points corresponding to y equaling 0, I have 0 for x, 0 for y, and I also have 2 for x, 0 for y. Okay, so that was the information that was given from me when y equals 0. Now when x equals 1, plugging x equals 1 into this equation, let's do that. So when x is equal to 1, I get 1 squared plus 4y minus 2 times 1 equals 0. So 1 plus 4y minus 2 equals 0. So 4y minus 1 equals 0. So y is equal to 1 over 4. Okay, so when x is 1, y is 1 over 4. So those are my three critical points right here. And I'm going to leave it up to you guys as an exercise to test these points. What you should get, I have the answer. Let me show you what you should get. You should get that this is a saddle point. This is a saddle point. And the third one is a local minimum. Alright guys, thanks for watching. I hope you guys enjoyed the video. I'll see you guys next time.